Hello, Math 200 students. We're moving into Chapter 3. Chapter 3 is all about probability. And to do probability, we're going to have to learn how to count. I know that sounds strange. We're going to have to learn how to count a lot of things. We're going to have to learn kind of some shortcuts of how to count a lot of things. So let's get into this chapter, section 3.1. When weather forecasters say that there's a 90% chance of rain or you have a 35% chance for successful surgery, then we're speaking about likelihood or probability that a specific event will occur. Decisions can be based off of probabilities. In fact, decisions should be based off of probabilities. You need to live your life according to probability. If you play against probability with your life, eventually you're going to lose. So you want to align your life with good decisions that where probability is in your favor. You want probability to be in your favor. I always like to start off this kind of a lesson with that. Probability can help with wisdom. All right, a probability experiment is an action or trial through which specific results, counts, measures, or responses are obtained. The result of a single trial in a probability experiment is an outcome. The set of all possible outcomes of a probability experiment is the sample space. An event is a subset of the sample space. It may consist of one or more outcomes. All right, let's look at example 1. A probability experiment consists of tossing a coin and then rolling a 6-sided die. Determine the number of outcomes and identify the sample space. Okay, so to identify the sample space, we want to identify, let's look at that definition again. The sample space, the set of all possible outcomes of a probability experiment. So we want to figure out the entire number of possibilities for this experiment of tossing a coin and rolling a 6-sided die. So here's a good tree diagram that they've drawn for you. You would probably want to draw this on your paper if you were trying to figure out the total number of possibilities. Of course, we'll actually learn some shortcuts to this too. But one possibility, if you flip the coin, is you get heads, and then if you get heads with the coin, how many you get? You could do a 1, 2, 3, 4, 5, or 6 with the die. So you could get heads 1, heads 2, heads 3, and so on. Or if you get tails with the coin, then you can get 1 through 6 with the tails. So T1, T2, T3, all the way to T6. So how many total possibilities are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The sample space has 12 outcomes, and we list them all right here. H1 through H6, T1 through T6. So just want you to know that each one of these, like H1, that is a specific outcome. H2 is an outcome. H3 is an outcome. All of these are separate outcomes, and there are 12 separate outcomes in the entire sample space. All right. An event, which is very related to an outcome, but a little bit different, an event can be just one outcome, or it can consist of more than one outcome. Like we could say, what is the probability of the event that you get a heads and a 5? Well, that's H5, right? That event is just H5, and so the probability of that event, which we hadn't really gone over that yet, would be 1. There's only one way to get H5, and it would be out of 12 different total possibilities in the sample space, so 1 out of 12. Or we could say, what is the probability of the event that you would get heads and an even number? So then the event's not just one outcome. The event would be H2, H4, and H6. The event could be 3 different outcomes in that one event that we categorize as heads and an even number. So you see the difference there. An outcome is just one thing, whereas an event can be one thing, or it can be more than one thing, depending on how we describe the event. Okay. All right. Maybe you could look at this and do the try it yourself ones to see if you understand what's going on there. In the rest of the chapter, you will learn how to calculate the probability or likelihood of an event. Events are often represented by uppercase letters such as A, B, and C. An event that consists of a single outcome is called a simple event. For example, tossing a heads and rolling a 3. That's a simple event. It can be represented just as the event A, capital A, equals just H3. In contrast, the event tossing heads and rolling an even number is not simple because it consists of more than one possible outcome. It consists of 3 possible outcomes, but it can also be represented with a capital letter. Let's call it B. And then in that case, B would equal H2, H4, and H6. So that's a simple event. Is when you just H3, if it's just one outcome, that's a simple event. But if it's more than one outcome, that would not be a simple event. All right, let's look at this one. Number 1, decide whether the event is simple, or determine the number of outcomes and decide whether the event is simple or not. All right, for quality control, you randomly select a machine part from a batch that has been manufactured that day. Event A is selecting a specific defective machine part. All right, I believe we would say that there's just one outcome because it says a specific defective machine part from just one batch. So just one specific machine part that we're looking for would be just one outcome, and I believe that would be a simple event. All right, you roll a 6-sided die. Event B is rolling at least a 4. All right, not a 4, but at least a 4. At least a 4 means 4 or more, 4, 5, or 6. So that is not a simple event. It would be 3 different outcomes, 4, 5, or 6. All right, the fundamental counting principle. This is going to teach us how we can count a lot of things quicker. In some cases, an event can occur in so many different ways that it is not practical to write out all of the outcomes, like we did with the coin and the dice. It was easy to list all those possibilities. It was just 12 of them. But sometimes, most of the time, it's not practical to write out all the different outcomes because there's so many different possible outcomes. When this occurs, you can rely on the fundamental counting principle. This can also be used to find the number of ways 2 or more events can occur in sequence. All right, here it is. If one event can occur in m ways and a second event can occur in n ways, the number of ways the 2 events can occur in sequence is m times n. This rule can be extended to any number of events occurring in sequence. In words, the number of ways that events can occur in sequence is found by multiplying the number of ways one event can occur by the number of ways the second or third or fourth or whatever event can occur. All right, so let's go back to the previous example. How many ways can flipping a coin occur? Heads or tails? 2 ways, right? How many ways can rolling a die occur? 6 ways. So how many ways can you do both of them together? 2 times 6, which is 12. All right, you are purchasing a new car in this example. The possible manufacturers, car sizes, and colors are listed. So you got 3 manufacturers for this choice, Ford, GM, and Honda. You have 2 sizes, compact and midsize. You have, 4 colors, white, red, black, and green. So how many ways can you select a car from all these choices? Well, 3 times 2 times 4 would be 48, right? 24. 3 times 2 is 6 times 4 times 4 is 24. 3 times 2 is 6. 6 times 4 is 24. Yeah. If you were to try to write it all out, it would be very tedious, but you could. Here's 3 doors. You choose to walk through the 3 doors of the car manufacturer. Then after that, pick that door. You got 2 doors for the size. Then after you pick that door, then you got 4 doors each for the colors. All right. Next example. The access code for a car's security system consists of 4 digits. Each digit can be any number 0 through 9. All right. All right, so a lot of times I like to just put blanks like this. We got 4 digits, right? How many choices do we have for the first number in this, the first digit in the security system? Well, they can be 0 through 9. That's actually 10 choices. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10 choices. So we got 10 choices for the first one. How many choices? I forgot to read these stipulations down here. Number 1, each digit can be used only once and not repeated. So we have 10 choices for the first digit. It can be anything. But then for the second digit, we can't use the same one we just used. So how many choices do we have for the second digit then if once we've already picked the first digit? We now only have 9 choices. And so now we can't use what we just used here in the first one or what we just used in the second one. So now we're down to what? We're down to 8 choices. And we can't use that one. So now for the fourth digit, we only have 7 choices. So 10 times 9 times 8 times 7, whatever that comes to, 5,040. Would be the answer to that first one. All right, number 2. On number 2, each digit can be repeated. So we got 10 choices for the first one, and then it doesn't matter what we pick for the first one. We still got another 10 choices, and another 10, and another 10. So that would be 10 to the fourth, right? Which would be 10,000. So 10,000 choices in that problem. Each digit can be repeated, but the first digit cannot be 0 or 1. So how many choices do we have for the first digit if it can't be 0 or 1? We have 8 choices. But the second digit can be anything, so it's 10 choices, and you can repeat, so 10 choices, 10 choices, 10 choices. All right, so now we got 8 times 10 to the third. That would be 8,000. Okay. All right, there are 3 types of probability, actually. Classical probability, empirical probability, and subjective probability. The probability that event E will occur, we usually write that as P with the parentheses with an E, and we say P of E, or probability of event E. All right. Classical or theoretical probability, classical or theoretical, those are the same thing, is used when each outcome in a sample space is equally likely to occur. The classical probability for an event E is given by the number of outcomes in event E divided by the total number of outcomes in the sample space. So example 5, finding classical probabilities. You roll a 6-sided die, find the probability of each event. Rolling a 3. All right, rolling a 3. What is the number of outcomes in that event of rolling a 3? There's only one outcome where you roll a 3. What's the total number of outcomes when you roll a 6-sided die? Well, there's 6 different total outcomes in the sample space. So the probability of rolling a 3 is equal to 1/6. Or if we got that as a it would be 0.167. Or if we wanted to write it as a percent, about 16.7%. About a 16 or 17% chance that you roll a 3. All right, what about rolling a 7? Well, how many outcomes would there be where you would roll a 7? None, right? There would be 0 outcomes where you roll a 7 out of 6, which would be 0. No chance of rolling a 7. What about rolling a number less than 5? Well, how many outcomes would you roll a die that would be less than 5? 1, 2, 3, 4. 1, 2, 3, 4. So 4. So 4 out of 6, which would reduce to 2/3, or 0.667, or 66.7%. All right. So you can give these probabilities as fractions, or as decimals, or as percents, and they're all the same thing. They're all correct. You just got to be aware of what the assignment is asking you, how it wants the answer written. So Math Excel usually tells you that. All right, next, we deal with empirical or statistical probability. When an experiment is repeated many times, regular patterns are formed. These patterns make it possible to find empirical probability. Empirical probability can be used even when each outcome of an event is not equally likely to occur. All right, so you can use empirical or statistical probability based on observations obtained from probability experiments. The empirical probability of an event E is the relative frequency of event E. All right, so relative frequency is something that we did back in chapter 1. Maybe it was chapter 2, I don't remember. I think it was chapter 2. Okay, so this is interesting to me because we're talking about at least two different kinds of knowledge here. So one kind of knowledge is your rational, logical way of knowing things, like the six-sided die. So we can just use our logic that there's one way to get 3 and there's 6 total ways, so 1 out of 6. Empirical probability is a different way of knowing things. It's using your senses, not your logic, but your senses. You're observing things in some sort of way. Sight, touch, taste, sound, all that. And that's called evidence, right? You gather evidence. You're looking for things through your ways of observation. And that's called empirical knowledge. All right. That's actually what science is. So the rationality or logical way of knowing things, that's philosophy. Whereas the empirical, statistical, observing way of knowing things, evidence-based, that's what science is based on. And those two things should always work together. And there's actually another way. I won't say it in this video, but there's another way of knowing things that I think actually justify these other two. If you want to know that, you'll have to ask me sometime outside of class. Okay, so example 6, finding an empirical probability. A company is conducting an online survey of randomly selected individuals to determine how often they recycle. So far, 2,451 people have been surveyed. The frequency distribution shows the results. What is the probability that the next person surveyed always recycles? Okay, so we use now what we have observed. We're not. It's not like the die where we're just using just straight up rationality or logic. We actually have to observe these things and then base it on that. So 1,054 out of 2,451 so far, that's what we've observed. So our best way of predicting is to base it all off of those observations. We would predict that the probability that the next person always recycles is 1,054 out of 2,451. 1,054 divided by 2,451. If we do that, we get 0.43, or about a 43% chance that the next person we survey will be one that always recycles. Okay. Using a frequency distribution to find probabilities. A company is conducting a phone survey of randomly selected individuals to determine the ages of social networking site users. So far, 975 social networking site users have been surveyed. The frequency distribution at the right shows the results. What is the probability that the next user surveyed is 23 to 35 years old? All right, all we would have to do, again, is use what we've already observed. So far, 312 fit in that category out of a total of 975. So 312 out of 975, you divide it, you get 0.32 or 32%. All right. This is a very interesting concept. As you increase the number of times a probability experiment is repeated, the empirical probability of an event approaches the theoretical probability of the event. This is known as the law of large numbers. Okay? So, if we toss a coin, all right, and we get heads, then so far, we've got 1 out of 1 as heads. That's 100%. So the empirical probability of getting heads would be 100%, whereas the theoretical probability of getting heads is 50%. But then we toss the coin again. We might get heads again. And so it still may be 100%, but we toss the coin again. And the more we toss the coin, eventually it's going to approach, if it's a fair coin, it's going to approach that theoretical probability the more you toss the coin, because you're not going to get 1,000 heads in a row, are you? I mean, if you do, it's time to start thinking, what kind of a day am I living in, right? So you will toss the coin 1 billion times, and it's gonna, the more you toss it, the more it's gonna hover at the 50% mark. All right. As an experiment is repeated over and over, the empirical probability of an event approaches the theoretical probability of the event. Okay. The third type of probability is subjective probability. Subjective probabilities result from intuition, educated guesses, and estimates. So some people would even put intuition as another way of knowing things. I don't know that I would, I'm not even sure that that really counts. Your intuition, of course, you can be wrong on any of these things if you make a mistake, but I would want intuition to be backed up by logic and or data evidence and such. But subjective probabilities result from intuition, educated guesses, and estimates. Sometimes that's all we have. Like if I said, what's the probability that you're going to, let me think. Like, what's the probability that I'm going to like what you just made me to eat? Well, I might take a look at it, see what it is, and I might base my intuition of the probability of what I'm gonna, whether or not I'm gonna like that, on just kind of my intuition about it, because I don't have any other way to base it. So, the example they give, for instance, given a patient's health and extent of injuries, a doctor may feel that the patient has a 90% chance of full recovery. So he hadn't really based that on fully on logic or fully on observations. He's got some logic and he's got some observations in his past, and those things are contributing to his intuition. But he's not like completely basing that on those things. Or business analysts may predict that the chance of the employees of a certain company going on strike is 0.25 or 25%. Again, he can't know that for sure, but it's an educated guess on his part, based on things that he's observed, based on his logic, but not fully based on that, purely based on that. All right, so look at example 8. You're going to read these things and you're going to say whether or not they're using classical, empirical, or subjective. And remember, classical is the same thing as theoretical. Empirical is the same thing as statistical. Subjective is the same thing as intuition. All right. Number 1, the probability that you will get an A on your next test is 0.9. Well, I don't really like the way that question is worded, because it's not telling you what you're basing it on. If you look at all your past tests and you say, well, I've gotten an A on 90% of my tests in the past, then it's going to be an empirical probability. But I think they're saying that you just have an intuition that you just kind of feel like you have a 90% chance of getting an A on that next test, which would be subjective probability. Number 2, the probability that a voter chosen at random will be younger than 35 years old is 0.3. Okay. That sounds like an empirical probability to me, based on the observations of what the voting population, the demographics of the voting population. All right. Number 3, the probability of winning a 1,000 ticket raffle with one ticket is 1 out of 1,000. That is classical probability. That's just doing the logical math of it. One ticket out of 1,000. Okay. A probability cannot be negative, and it cannot be greater than 1, as stated in the rule below. Probability of event E is always between 0 and 1 inclusive. That is, probability of event E is greater than or equal to 0, less than or equal to 1. All right. When the probability of an event is 1, the event is certain to occur. When the probability of an event is 0, the event is impossible. A probability of 0.5 indicates that an event has an even chance of occurring or not occurring. The figure below shows the possible ranges of probabilities and their meanings. So 0 being impossible, 1 being certain. Right there in the middle means it's an even chance. Could go one way or the other with an even chance. If you're less than 0.5, it's unlikely. If you're more than 0.5, it's likely. Okay. An event that occurs with a probability of 0.05 or less is typically considered unusual. Unusual events are highly unlikely to occur. Later in this course, you will identify unusual events when studying inferential statistics. I would really like to talk more about probability and philosophy. I may do that in a special video. Haven't decided yet. We'll see. All right, the sum of probabilities of all outcomes in a sample space is 1 or 100%. All right, let me just say this real quick. Some of you may be confused. If it's between 0 and 1, then how can we say something like 50%? That's more than 1. No, it's not. 50% means 50 per 100. Percent means per 100. It means percent means divided by 100 is what it means. So when you're doing a percent, that's already saying it's divided by 100. So 50% means 50 divided by 100, which is 50 over 100 or 0.5. So percent is a decimal that's, so it is less than 1 in that case. All right, an important result of this fact is that when you know the probability of an event E, you can find the probability of the complement of event E. So the probabilities of all outcomes in the sample space, all of the probabilities in the sample space add up to 100% or add up to 1 if it's a decimal. So if you know the probability of event E, you can find the probability of the complement, meaning not E, the opposite of E, something that's, so getting heads or not getting heads, rolling a 3 or not rolling a 3. Those would be complementary events, complements. The complement of event E is the set of all outcomes in the sample space that are not included in event E. The complement of event E is denoted by E with this dash. We call it E prime. E with the dash mark is called E prime, and it's talking about the complement of E. All right, for instance, when you roll a die and let E be the number is at least 5, then the complement of E is that the number is less than 5. So at least 5 means 6 means basically 5 or 6. The complement of that would be anything but that. So 1, 2, 3, or 4. So E would be 5 or 6. E prime would be 1, 2, 3, or 4. Using the definition of the complement of an event and the fact that the sum of the probabilities of all the outcomes is 1, you can determine the formulas below. Since all of the probabilities must equal 1, the probability of E plus the probability of E prime has to equal 1 because it's either E or it's not E. So it's either going to be 5 or 6 or it's going to be not 5 or 6, which is 1, 2, 3, or 4. So add those two things together, it's always going to equal 100% or 1. All right. So that means the probability of E is always 1 minus the probability of E prime, or vice versa. The probability of E prime is always equal to 1 minus the probability of E. The Venn diagram at the left illustrates the relationship between the sample space and event E and its complement. So here's E, 5 or 6, and E prime is 1, 2, 3, or 4, and 1, 2, 3, 4, 5, and 6 is everything in that whole rectangular sample space. All right. The probability of the complement of an event. Use the frequency distribution in example 7 to find the probability of randomly selecting a social networking site user who is not 23 to 25 years old. So looking back at this example 7, not 23 to 25. What's the probability that the next person is not 23 to 25? Well, one way we could do that would be to add up all these things that are not 23 to 25. We could say 156 plus 254 plus 195 plus 58. And then put that result over the total 975. But the other way that might be quicker, and it is very much quicker in a lot of cases, is if you know 23 to 35 is 312 over 975, just subtract that from 1 to get your probability of not being 23 to 35. So that's what they did here. They knew they already did that. It's 0.032 is 23 to 35. So not being 23 to 35 is 1 minus that, which is 0.68. Of course, you could also do it with the fraction. All right. Using a tree diagram. A probability experiment consists of tossing a coin and spinning the spinner shown at the left. The spinner is equally likely to land on each number. Use a tree diagram to find the probability of each event. Event A, tossing a tail and spinning an odd number. Okay, so we can look at this tree with all these outcomes. Tossing a tail, and what was it? And spinning an odd number. So T1, T3, T5, T7. 1, 2, 3, 4 different ways that can occur. How many ways can it occur altogether in the sample space? Total possible outcomes would be 2 times 8, right? Two ways to do the coin, heads or tails, 8 ways to do the spinner, so 2 times 8 is 16. So we got 4 out of 16, which reduces to 1 out of 4, or 0.25, or 25%. All right, this next one is a little confusing. All right, event B is tossing a head, all right, or spinning a number greater than 3. The first one was tossing a tail and getting an odd number. So it had to be T1, T3, T5, T7, but this is tossing a head or spinning a number greater. So tossing a head would be any of these, right? H1, H2, H3, all the way to H8. Or spinning a number greater than 3. Well, that would be H5, H4, H5, H6, H7, H8. But we've already counted those when we. So these would be included in tossing a number greater than, spinning a number greater than 3. But we've already counted them, so we don't count them twice. So, but then the tails, all the ones that are tails that are greater than 3. So T4, T5, T6, T7, and 8 have to go in there too. So count all those up together, and that's 8, 9, 10, 11, 12, 13. So 13 out of 16, or 0.813, or 81.3%. All right, example 11, using the fundamental counting principle. Your college identification number consists of 8 digits. Each digit can be 0 through 9, and each digit can be repeated. What is the probability of getting your college identification number when randomly generating 8 digits? In other words, what's the probability of somebody like basically guessing your college ID? So 8 digits. All right, 1, 2, 3, 4, 5, 6, 7, 8. And how many choices do we have for the first digit? 10. They can be repeated. So how many for the second digit? 10. 10, right? All the way down. That's going to be 10 to the what? To the 8th. So there's 8 different 10s that multiplying together. So that's going to be, let's see, 1, 2, 3, 4, 5, 6, 7, 8. 100 million. So the probability of them randomly guessing your ID number with the first guess would be what? Would be 1 out of 100 million. All right, so that finishes us up for 3.1, which was the basic concepts of probability and counting. Good luck on 3.1 homework. I'll see you again in 3.2.